Great Orbax, and we're here today with Raul, a graduate student in the nanoscience program, to discuss the science behind flying saucers in pulp culture. So Raul is going to demonstrate for us some different mechanisms by which a little tiny saucer might give rise to levitation of our little green man.
All right.
Get right into it, Raul!
Okay. Over here, we have a type 2 superconductor made out of yttrium, barium, copper oxide. When exposed to a magnetic field, there's a breakthrough at certain points in its crystal structure that causes it to be pinned in place, and that causes it to levitate.
So physically, the magnetic field is holding that structure up in the air.
Yes, it is.
And it's an invisible field that gives us true levitation.
Exactly, yeah. So it's supported by the force of the magnetic field repelling the superconductor, and that's in balance with the force of gravity pulling it down.
And the idea behind this is that it needs to be at extremely low temperatures for this superconduction to take place.
Yes, normally we use liquid nitrogen to do this, which is at 77 K. It stops being superconductive at 92 K.
From magnetic superconductors, we now turn our gaze to harnessing the awesome power of sound.
So we have two sets of transducers playing high-intensity, high-frequency audio 180 degrees out of phase. This creates a standing wave, which allows very light pieces of foam to levitate as they sit on a cushion of high-pressure air.
So, and again, this is levitation. That's true levitation. You know,
yes.
you move your hand underneath and above. There's no strings attached.
No strings.
And this is working on this idea that we're generating a standing wave, so that we have regions of high pressure, regions of low pressure. You're physically trapping this foam in a region where the molecules of air aren't really moving that much, but are bordered by regions where they move a lot.
Yes, so if this was in space, it would be floating right in the low pressure region, but because we're on Earth and we have gravity, it actually sits on the area of high pressure, like a cushion.
And this is a direct application of stuff that we learn about in our first year physics courses here at U of G.
Yeah, you do.
Now this example is a different type of magnetism called diamagnetism. Raul, what's involved with this?
So what we have here is two pieces of bismuth that provide diamagnetic repulsion to a small magnet that we place in between them. Normally, if you just try to suspend a magnet in midair and use another very strong magnet to hold it up, you can't actually get it to levitate stably because of Earnshaw's theorem. And what that says is that there's no stable equilibrium point in that case. But by providing diamagnetic repulsion due to bismuth, we can create a stable region of levitation using this very strong magnet.
So you're telling me that the object itself has to be magnetic.
Yes.
We have to provide a super strong magnet.
Yep.
And then the lower case is
2 chunks of bismuth.
just 2 chunks of bismuth. So
So
that's
if we-
the bismuth. Okay.
Yeah, so if we think of force balance, we got force of magnetism pulling it up, force of gravity pulling it down, and then force of diamagnetism repelling it up and down creates a stable equilibrium point. In our NMR spectrometer that we have in the Summerlee Science Complex, we can maybe get a frog to levitate, but a cow, I don't know about that.
So in movie after movie throughout the years, we've seen our flying saucers, our UFOs, our UAPs, levitating and flying through our nighttime skies, and sometimes daytime skies as well. While we may not be able to make a ship of that size float in the air, we've got 3 different scientific methods of making something levitate. So is the science of flying saucers real or unreal?
We can do frogs, green frogs.
Well, we can do frogs. God, this book reeks. It just stinks so bad. It's weird. Usually flea market books smell so much better.